Hello, Year 12s. We have now done amines and we are going to be doing amino acids next and amides. I'm going to start off with amides because there is a natural link with amines, and then I will go on to amino acids. So it's a tiny bit different from your textbook. The order is different, that is. Okay, let's start. So I'm going to start off with the question, describe reactions of amines to make amides. Now, this is not as obvious in the textbook as it might seem. There's literally a couple of lines on page 480 under the heading amides on this, so it might not seem obvious to you at all, but I've taken this opportunity to talk a little bit about it. I will then go on to drawing the primary, secondary and tertiary amides, and I will then go on to the beginning of the chapter on amino acids. So a bit of to and froing within the chapter. So I think this will be a sort of topic where you'd want to take extra notes because I a little bit extra. Right, so this is the structure of amides. It's a derivative of carboxylic acid. That means that if it is hydrolyzed or reacted with water, it would form carboxylic acid, like acyl chlorides, like esters. There are two ways of making amides. These reactions equations even are not in your textbook, so please copy it down. You've got on the left an acyl chloride. It's ethanoyl chloride. It's got 2 carbon atoms, and ammonia. Now, couple of things. You see a nitrogen atom, please put a lone pair down. And also, as you know from year 12, the shape of ammonia is trigonal pyramidal. So that shape that I have put in front of you from Google is incorrect. It's pyramidal. So when you're drawing this, please make sure you've got lone pairs on the nitrogen atoms and that it's a pyramidal shape. Now, if you can imagine this, the lone pair on the nitrogen will form a dative covalent bond with the carbocation on the ethanoyl chloride. Because of the electronegative atoms oxygen and chlorine on the acyl chloride, there are delta negative charges on these two atoms and a delta positive charge on the carbon atom. So a dative bond will form between the nitrogen of ammonia and the carbon delta plus to make the amide. So amides can be made by the reaction of ammonia with an acyl chloride very quickly. Chlorine is a very good leaving group, so it's a nucleophilic substitution reaction. That's a good word to use in this. I haven't got it on this slide, but it does do nucleophilic substitution reactions to make amides. The other way of introducing that NH group is to make an amide is by reacting an acyl chloride with an amine. In this case, it's a primary amine. So that's the second way. And if you have an excess of the amine or an excess of an ammonia, you get the amide. In this case, at the bottom, remember about remember to count carbon atoms. So you've got ethanamide takes the carbonyl group takes priority. So if you start with the carbonyl group, it's 1, 2. So it's ethanamide with the amide there. Okay, so ethanamide, and then you got the branch, which is N-ethyl, 2 carbon atoms at each. Remember, end of each line is a carbon atom each. N-ethyl and ethanamide is your product. Okay. Right, so it's an example of something that's a little bit more complex. I think, to be honest, we've done something that started off with something that you might not have in your textbooks, but I'm certain on to drawing primary, secondary, and tertiary amides. So we've made the amides in 2 ways. How can you draw it and name it? So if there is, if we say the R in these structures is C3H7, so it's propyl. Okay, it's a propyl group, but please remember that there is a CO there as well that we have to take into account. So C3H7 on the R group plus the C from the CO makes it 4 carbon atoms, which makes it butanoyl amide. Okay, so that would be butanoyl amide, where the nitrogen atom, it's a primary amide, the nitrogen is attached to 1 carbon atom. Now, if the nitrogen atom, note the lone pairs, please put it in a highlighter if you haven't already. If the nitrogen atom is attached to 2 carbon atoms, then it's going to be a secondary amide. And as you know, try pause this video to name these structures if you like. This structure is going to be N-methyl N-butanoyl amide. Now we've got a tertiary amide where all the hydrogens are replaced and are now attached to carbon atoms. So all 3 bonds on nitrogen are attached to carbon atoms. So this amide is going to be called, pause the video, figure it out, N comma N dash dimethyl butanoyl amide. Okay, so you are now going to be doing an exercise, and you are now going to be drawing these 3 structures. Please pause the video. Okay, the first structure, as you can see, is butanamide. 1, 2, 3, 4 carbon atoms. When you are drawing these skeletal structures, please do not have a CH3 at the end. Okay, some of these images that you see in textbooks and websites are incorrect. This is a skeletal formula and you cannot have the CH3 at the end, so do not add on the CH3, but instead leave it with nothing there basically, so you can see. So the next structure is correct as a skeletal formula. This is N-methyl butanamide. Okay, so N is attached to a methyl group on the left, and on the right you can see the 1, 2, 3, 4 carbon atoms. It's a butanamide. And then finally you've got your tertiary amide. So the first one is a primary, second one is a secondary, and the third one has nitrogen atom attached to 3 carbon atoms. So it's going to be NN-dimethyl butanamide. Okay, so we are now going to go on to amino acids, which finishes off our carboxylic acid derivatives. And we are now going to be looking at something that is found in nature, in plants, in animals, as you know from biology perhaps, that has an amine group and also has a carboxylic acid group. So it's quite unique, and we're going to be looking at the structure and reactions and so on. So let's describe amino acids. It has both NH2 and COOH groups. The NH2 group is basic. It has a lone pair that is a proton acceptor. And the COOH is acidic. Okay, it is able to donate H plus or protons, which makes it acidic. Our body, the human body, has 20 alpha amino acids. The 20 amino acids are different from each other because they have some different R groups. I'll talk about R groups in a minute. Define alpha amino acids. So the examples that I've given on the left is an example of an alpha amino acid. An alpha amino acid is where the amine group in blue is one carbon away from a carboxylic acid group. So an amine is on the alpha carbon or the carbon next to the carboxylic acid group. Now this is different from another type of amino acid called beta amino acids. Here the amine group in blue is has 2 carbon atoms between it and the carboxylic acid group. Okay, so in the case of the alpha, there is 1 carbon atom between the amine and the carboxylic acid group. In the case of the beta amino acid, there are 2 carbon atoms between the amine and the carboxylic acid group. Amine is bonded to the 3rd carbon. Okay, so in alpha amino acid, its amine is bonded to the 2nd carbon atom. In the case of the beta amino acids, it's bonded to the 3rd carbon atom. And there are some examples I've shown at the bottom. Same example again here. Right, so we are now going to look at the reactions of amino acids, and they're interesting because they've got a basic group, which is your NH2, and they've also got an acidic group, which is your COOH. Please remember to put a lone pair on that NH2, like we agreed to do a while back. Okay, so describe the reaction of the amine in amino acid. In this case, the amine and the amino acids itself is reacting with hydrochloric acid. Now, acids react with bases. Acids do not react with acids. Acids react with bases. So the lone pair on the nitrogen is going to form a dative covalent bond with the hydrogen. The hydrogen atom or proton is going to be, the nitrogen atom is going to be a proton acceptor and forms a dative covalent bond. So this will then go on. This is what we call an acid-base reaction, and it's going to form an ammonium salt. It is not a neutralization reaction. Pause the video and think about why that is. This is because it is not a neutralization reaction because water is not made. Water is neutral and water is not made in this case, so it is an acid-base reaction. Right, next we are going to look at the reaction of the carboxylic acid groups in amino acids. Now, I'm sure you can understand that because it's acidic, it's probably going to be reacting with something basic. And also, this is a good time to think back to those reactions of carboxylic acids that you did a few lessons ago, like reactions with alcohol, right? Like reactions with metal, metal oxide, metal hydroxide, and metal carbonates. Okay, these are 5 reactions, and the way I remember it is because I know my GCSE work, and at GCSE you learnt about the reactions of acids. It's a reaction of acids with metal, metal oxides, metal hydroxides, and metal carbonates, and 3 of those are neutralization reaction. Metal and acid is not a neutralization reaction because hydrogen gas is made. And the last reaction is esterification, and that too you learnt at GCSE. So here we go, GCSE again. So neutralization of carboxylic acid with sodium hydroxide this time makes the sodium salt plus water. So really, GCSE work. And here is an example. Have a look at this yourself. It's something to think about. Okay, define stereoisomers. Stereoisomers are any compounds with the same structural formula but a different arrangement of atoms. And you can see here, this carbon atom in the middle has 4 different groups attached to it. It also has 3 different types of lines: the dotted line, a very solid wedge, and a single line. These show, like we learned in year 12, the dimension. It gives dimension to this compound. From now on, year 12s, you are going to be drawing these wedges every time you come across an atom that has 4 different groups on it. Okay, this is really important. It's an easy mark, and that makes it very important because you can get these little, you can get these things easily correct. Just like I said, whenever you see nitrogen or oxygen or fluorine, put those lone pairs in. Here, when you see 4 different atoms, types of atoms around a carbon atom, please put the different types of. Optical isomerism is a type of isomerism found in molecules with a chiral center. So, what does a chiral center mean? A chiral center is a carbon atom with 4 different groups attached. And what these do is that they form mirror images of each other. Okay, and we'll look more into this in the next slide. So you can show a chiral center with an asterisk. When you see a chiral center, you're going to be doing a number of things. You put an asterisk on it, but you have to put the 3 different wedges. There is one more thing I want you to remember before you look at your exercise on chiral centers that you printed out last lesson and you might have already attempted. Chiral centers do not have double bonds. So if you see a double bond, the carbon atoms in that double bond are not chiral. So, a couple of things to take away. Chiral centers have 4 different groups attached to it. If you see a chiral center, asterisk it, put different bonds on it. These chiral centers will go on to form optical isomers. It's a type of isomer found in molecules with chiral centers like the one you see here on this slide. Okay, so we are now going to come across the word enantiomers. Enantiomers, the chiral carbon atom in a molecule makes it possible for two non-superimposable mirror images structures to exist. Now, this might seem like a difficult definition, so let's break it up. Let's look at your hands. Your hands are chiral in the sense that they are very different all throughout. One hand has different, they're not symmetrical. If you look at one hand of yours, it is not a symmetrical structure. It's all got very different points all around it. Your right hand is also the same. It's a mirror image of your left hand. And if you get those two chiral, and if you get that chiral molecule and its mirror image, which is your left and your right hand, and you put it on top of one another, okay, they are not superimposable. That means your thumb does not line up with your thumb. Is not on top of the other thumb. Your little finger is not on top of the other little finger. They're all mismatched, so it is not superimposable. And this principle is the same for chiral molecules. A chiral molecule with an asterisk on the carbon and 3 different wedges for the atoms, because they have 4 different groups around a carbon atom, forms a mirror image like the one you see. But when you get the 2 molecules, the mirror image and the original molecule, and you take it out of the mirror, and you put it on top of your original molecule, they will not sit directly on top of each other. The H would be on the mirror image, will be on top of the CH3, CH2, and it'll be same for the other one. And they just won't sit right. Okay? So they will not overlap. And that is what non-superimposable means. They do not overlap. So you should have done an exercise that was given to you on a printed sheet, and you were asked to identify all the chiral centers with an asterisk. So that's what you're going to be doing. You're going to be marking your work now. So I would strongly recommend to go back through that sheet. If you've marked anything with a double bond as a chiral center, you now know that that cannot be the case. Go from one end of a molecule to the next, identifying the each carbon atom. So for example, for the structure on the left, which is spearmint, I would probably start from carbonyl group. Is that carbonyl group a chiral center? Then I go clockwise where the methyl group is, and a double bond. Is that a chiral center? Then I go to the next carbon atom where there's still a double bond. Then I come down. Remember skeletal formula. Okay, if you see a joint like that, okay, what does that mean? It means that that carbon atom is joined to 2 carbon atoms, and it also has 2 more atoms that you cannot see. They are hydrogen atoms. Okay, so it's got 2 hydrogen atoms on that carbon, and it's also bonded to 2 carbon atoms. Come down, right down, where you've got a center there with not only wedges, but it's bonded to 2 carbon atoms, which have in itself different things attached to it. It's attached to a hydrogen atom there, and it's attached to a branch there as well. So all these things matter. And then finally come up again to next to the carbonyl group again. Is that a chiral center? There are 3 other carbon atoms in the branch below, very near the word spearmint. Are those 3 carbon atoms in that skeletal formula, one of which is a double bond, are they chiral centers? So in the next few slides, you will see the question, And then the following slide will give you the answer. So I will not be talking through the rest of for a while. I will just be scrolling down the slides to show you what's there. So at any point, please feel free to pause and do the problem, or if you've done the problem, you just need to mark now until we get to a point when I'll be teaching again on various other bits. Okay, so I hope that was useful. You will be getting questions on chiral centers in an exam. It's guaranteed. I see it over and over again. They'll give you some random structure you've never seen, and it's so important that you know that it exists. Chirality. In organic chemistry, chirality is found in sugars, proteins, and nucleic acid. Okay. Describe the chirality in alpha amino acids. So I'm going to give you 3 points about the chirality in alpha amino acids, and some of them towards the end are repeats of what I've said before. Number 1, carbon atoms in amino acids are chiral apart from one amino acid, which is glycine. Glycine is not chiral. All the others, it's got 2 hydrogen atoms. If you see those yellow boxes in the amino acids here, those are what we call the R groups. All the R groups are different. I know I said this right at the beginning. All the R groups are different for amino acids, for the 20 amino acids in our bodies. But there is one amino acid that has an R group of H, and that is glycine, and that makes that glycine not chiral. 2, any element can be chiral, not just carbon. Lone pair is one of the 4 example in nitrogen. So if you look at this one here, okay, that is a chiral center. All right. And I know I've shown you this before. Chiral centers are shown with stars. So important. You show wedges, and also elements with double bonds are not chiral.